In this video, I'll be giving a sample problem on Newton's second law with kinematics. So for the first problem, a waiter shoves a glass of liquor with a mass 0.35 kilograms along a smooth counter. The glass leaves his hand moving at 2.3 meters per second, then slows down as it slides due to a constant horizontal friction exerted on it by the countertop. It slides for 1.0 meter before coming to rest. What are the magnitude and direction of the friction force acting on the glass? So let's analyze the problem. Let's start first by writing down the given. So it says here that the mass of the liquor that we're dealing with is 0.35 kilograms. And then here, we're representing it with a box because we're actually doing a free body diagram to understand the scenario better. And then the initial horizontal velocity, or v sub 0x, or v naught x, is 2.3 meters per second, meaning to say when it left the hand of the waiter, this is the speed at which it was initially moving. And then the final horizontal velocity of this glass should be 0 meters per second because, as you can see, after moving for some time, it actually comes to rest. Next, the displacement along x, or d sub x, is 1.0 meter. Nothing bloody, it's directly stated in the problem that it covered 1.0 meter until it stopped. Next, the required to find, or RTF, is the frictional force. So it says here magnitude and direction of the friction force acting on the glass. So by impulse, we would think of the Newton's second law because we're solving for frictional force, and Newton's second law is that fundamental equation that deals with forces acting when you have a given mass. So let's try doing that first. Also, to add the frictional force to the free body diagram, it would look like this. So as you can see, the arrow is pointing left because if we are taking the motion of the glass to be in the positive x direction, it's moving this way, then the frictional force as an opposing force should be pointing in the opposite direction. So the free body diagram looks like this now. And then we know the fact that there are also vertical forces acting on it, but we don't care about this because the acceleration of these liquor glass is along the x-axis. So just for the purpose of completing the free body diagram, we're going to make it look like this. So you have the weight as well as the normal force against the glass. Next, going forward, let's try to solve for frictional force. So the equation for second law is sigma F equals ma. Take note that I just added the subscript x to specify that we're dealing with horizontal motion. So there's nothing bloody in there. Next, we know the fact that the forces acting along x is actually just nothing but the frictional force. So we can say that the sum of the forces along x is just the frictional force itself. And with that, we can actually rewrite the second law equation into this. So nothing bloody. It's just that, again, the only force acting solely along x is frictional force. So you can replace sigma fx in the equation with frictional force instead, okay? And that's what we're solving for. So that's a perfect way of writing the equation. And then we just affix the mass times acceleration expression. So let's try. If you plug in the given to solve for frictional force, it would be mass times acceleration. However, if you look at it, we only know the mass of the object, the glass, it's 0.35 kilograms, but we actually don't know the acceleration. So how do we deal with that? So again, aside from the fact that we've stated beforehand that it's a Newton's second law plus kinematics problem, you should actually recognize that you need to use kinematics for this because Newton's second law cannot take into account the acceleration of this problem. But if you look at your given variables, you have velocity values, you also have displacement, and you have to take note of the fact that these are kinematic variables. So you can use the kinematic equations for this. And again, if you try to solve for A using kinematics just to help this second law equation, you have to look back at our kinematic variables, and it's actually this set of variables. We have displacement, acceleration, time, and the velocity value. So if you look at our inventory of given, we have initial horizontal velocity. We know this in the problem. And then we also know our final horizontal velocity, which is 0. And then the displacement along x is also known. Now, we're trying to solve for the acceleration, so we can plug it in the second law equation. And then the missing variable here is actually time, right? So again, when you say missing variable, it's the variable that we're not solving for in the problem, but we also don't know its value. And I'm pointing out that time is our missing variable because you have to pick an equation which does not contain this missing variable. So if you look at our kinematic equations in here, just let me clean the board. Now take note that these equations are for constant acceleration, and it's applicable in the problem because the frictional force on our glass is constant. So if you have a constant frictional force acting on it, then acceleration must also be constant. So we can apply these equations. Now take note that we have to pick this equation because our missing variable is time. And again, whenever time is the missing variable, the goal is just to pick an equation which does not contain time. It's that simple. So that's our chosen equation now. Now, the next thing we're going to do is we're going to isolate a sub x because that's what we're solving for. So first, you have to cancel first vx squared because that is 0 in the problem. And then next, because this is separated with a plus sign, you can transpose v naught x squared on the left side of the equation. So it goes in here. It changes its sign whenever it crosses the equal sign. So it's now negative. And then you're going to have 2ax dx on the right side. Next, we're solving for a sub x. So you need to divide both sides of the equation by 2 dx to isolate a sub x. So it's going to look like this. Again, we just divide both sides of the equation by 2 dx. And then we can now cancel 2. We can now cancel v sub x. And then we have finally isolated acceleration along x. And our final working equation for acceleration is this. So nothing body, I just switch them horizontally. Acceleration equals negative v naught x squared over 2 dx. So this is our equation. Next, we plug in the given. So initial horizontal velocity is 2.3 meters per second, and then raise that to the second power. Do not forget the exponent 2. Now, be careful with this equation. You might be you might make the mistake of raising the negative sign to the second power, but that would be wrong. So in this equation, take note that you need to raise the velocity to the power of 2, and then you affix the negative sign. So in this case, for example, you have to do 2.3 raised to 2, and then whatever you get, you affix the negative sign, and then do the rest, okay? So the final answer you're supposed to get is negative 2.645 meters per second squared for the acceleration. Take note, I'm not applying yet the rules on significant figures because this is just the middle of the solution. So the final answer that we're looking for is the frictional force. So at this point, now that we know the acceleration and we have determined it using kinematics, we can now go back to our second law equation, which is still hanging in here. So again, frictional force is mass times acceleration along x. So you just need to plug in the missing acceleration value here, and that is negative 2.645 meters per second squared. You're supposed to get negative 0.93 newtons. For the significant figures, in multiplication, we follow the given with the least number of significant figures. So this is 2 significant figures, this is 4. So we follow 2 significant figures. And then for the unit, take note that whenever you multiply kilograms by meters per second squared, you will arrive at Newton because by definition, Newton is equivalent to kilogram meters per second squared. So that's our final answer. Is it reasonable? In terms of magnitude, yes, frictional force values are usually around less than 1 in terms of magnitude in newtons. And then for the sign, of course, it will be negative since, again, we take the positive direction as the motion of the liquor glass. So the friction force has to be opposite to that motion. So it has to be negative. So that's it. And then for the general problem-solving guide for Newton's second law with kinematics, you have to understand the problem as usual, draw a free body diagram so you can visualize it properly, and then identify the known variables and what you want to solve for. Then apply Newton's second law, use kinematics if you get stuck somewhere and you seem to be lacking known values for your second law equation. And then make sure that the units properly cancel each other out. Do not follow what other YouTubers do where they just say, oh, the final unit format should be this, it should be this. No, that's obviously wrong. You have to see that the units are properly canceling, etc. Okay, and then perform unit conversions whenever necessary. And then evaluate if your answer makes sense because it means that you need to judge if your answer is reasonable. Is the sign correct? Is it really supposed to be negative? Is the magnitude reasonable? Is it too high? Is it too big? Because if you ask yourself those questions, then you have an opportunity to question the correctness of your answer and review your solution if your answer do not look sensible. So you have better chances of getting it right. That's all for this video. Thank you for watching.